Kim Shepard again. We're back with lesson video 8B. Last time we looked at two variables and how we identify which variable is the explanatory variable and which variable is the response variable. Today we're going to pick up where we left off with that in this video and talk about how we'll graph those. We saw a brief glimpse of a scatter plot in the last video. So you always want to make a graph. And the correct graph that we'll make here when we're looking at the relationship between two quantitative variables will be a scatter plot. And as we mentioned in the last video, the explanatory variable is the variable that will go down on the x-axis, and the response variable is the one that will go on the y-axis. So this may be a little bit difficult to see, but this one we're using students' arm span to predict their height. So these are students' arm span, how big their arm span is, and we're using that to see if we can predict their height. These are all in inches. We mentioned last time it's really crucial that you identify the proper variable for x and y, and if you have it backwards, that could be an issue. This is one example. Now the statement says we're using arm span to predict height, so that's your indicator that arm span is the explanatory predictor variable, and what we're trying to predict, the response variable, is height. However, if we just said explore the relationship between arm span and height, you really could say, I'm going to use the height of a person to help predict or explain their arm span. So this is one where if it wasn't specified in this way, you could almost flip those variables around. Most examples, there's a particular variable that you're using to help explain or predict the other variable. All right. In video A, we looked at the direct loan problem. With the direct loan problem, the number of loans was the explanatory variable, so it's going to go down on the x-axis. And the loan value was the variable of interest. That was the response variable, so it goes on the y-axis. And now this time we took those 62 schools and we plotted each ordered pair of points and put that on what's called a scatter plot. If we wanted to make some comments on this scatter plot, we do sort of see a very nice pattern to these points. It looks like a straight line. So this looks like a linear pattern to the points. It looks like you could almost approximate the relationship by drawing a straight line there. That straight line goes in a positive direction. As the number of loans increases, the loan values tend to go up as well. So the direction here is positive. And the relationship looks pretty strong. Those points are pretty tight around this line. There's not a huge scattering to those points. And we could say with this one that there are a few outliers. You see that there are, remember this is 62 schools in this scatter plot. There's a lot of schools down here. A lot of schools that are smaller. Cecil College is somewhere down here. It's one of the smaller ones. But you see that there's a handful of large schools. So we could say that there was a handful of outlying schools that were some of the bigger schools. It's possible with this one that we really might have wanted to split the data set up and look at maybe community colleges as one set of data and larger four-year schools as another set of data. I kind of commented on some things about this scatter plot. In the next couple of slides, we're going to solidify that when you have a scatter plot like this, there's 4 comments we want to make. So with this one, we said that the pattern's linear. Looks like a straight line. The direction is positive. And that just means, if you're taking notes here, that as the number of loans increases, so does the loan value. The strength is pretty strong because those points are pretty close to the line. So the strength of the relationship is fairly strong. And we could say that the couple of larger schools here are outliers. Okay, so now we're going to to go through and comment on these 4 things in general, the 4 things that we'll use to describe any scatter plot that we make. And so every time you make a scatter plot, we'll be able to say 4 things about that scatter plot. And one of the first things that you want to comment on when you're looking at the relationship between your 2 quantitative variables is the form of the relationship. Is the relationship linear? Linear's got that word line in it. Does it look like those dots follow a straight line? Sometimes you'll have a relationship, it definitely looks like x and y are related, but the pattern of the points is not a straight line, maybe it's a curve. So your form could also be nonlinear. And then once in a while you'll have a scatter plot and it just kind of looks like somebody sneezed dots all over the page and there's nothing going on there. So no relationship. So we'll look at a few scatter plots and talk about the form. This is back to the one where we're using your arm span to predict your height. And this relationship here looks nice and linear. Not quite as strong as the direct loan problem. We'll get to strength in a minute, but the form of this is linear. Second one here, this is the year it is, and I'm not sure what the y variable is. It says that the slide maker forgot to tell me what the variable is, so I'm not sure what this is. Always title your graphs and label your axes, right? Good reminder. But the point with this one is, these points do not follow a straight line. It does look like they sort of follow a pattern, but definitely would not call this a straight line, so the form of this would be nonlinear. And then this one, we're looking at age versus height, and it doesn't look like there's any kind of definite relationship here between how old you are and how tall you are. These ages go from 15 years old to 45. Just sort of a random scattering of points. So we would say that the form of this one is there's no relationship to this one. So first thing you're going to comment on with the scatter plot is the form. The second thing that you're going to comment on is the direction of the relationship. And so the direction of the relationship can either be positive or negative. In our direct loan problem, scatter plot, the direction was positive. As the number of loans increased, so did the loan value. With arm span and height, this one is also a positive relationship. The bigger your arm span, those heights tend to also increase. So this is another example of a positive relationship. This is a negative relationship this time. This is the mileage on a car versus the price of a car. And this makes sense that the more miles on the car, the price of the car is coming down, is dropping. So as x is increasing, the y variable here is decreasing. So this would be an example of a negative relationship. So we've got form, we've got direction. The third thing we'll describe is the strength of the relationship. And for now, we'll use words like, to describe the strength, we'll say that the strength is strong, moderate, or weak. And strength is a measure of how scattered those points are. If your points are very tight around the line there, we have a strong relationship. If they're a bit more spread out, the relationship's more moderate. And if they become even more spread out, they're somewhat weak. This is kind of subjective using these. You can even say it's strong to moderate. And in a later lesson, we'll talk about a way to quantify the strength. We'll give a number to the strength in a little while. But for now, we're just going to describe these with words. So with the direct loan problem, we said we thought this relationship was pretty strong. It looks like if you drew a straight line, there's not a whole lot of scatter to those points. Those points are pretty tight along a straight line here. So this would be an example of a very strong relationship between two variables. This is arm span and height, and especially when compared with the previous scatter plot, the points are getting a little bit more spread out. So we might describe this one as more moderate. You could even say strong to moderate, but not quite as strong of a relationship as the previous scatter plot. This is for chicken sandwiches. This is the amount of sodium in there in each sandwich in milligrams. We're using that to predict the grams of fat. And there does appear to be a weak sort of positive relationship here. But these points this time, if you were to draw a straight line, they're getting to be much more scattered. So this relationship is very weak. All right, the fourth thing that we'll comment on with the scatter plot. We've got form, direction, strength. The fourth item, we'll look for unusual features. Are there clusters of points that require further investigation, or are there points that we might consider outliers? And if there are, we'll note them, and we'll proceed with caution. If there's no unusual features, that's fine too, but we'll make sure that we denote that this graph had nothing unusual about it, no unusual features. With the number of loans versus loan value, we made the comment that there were a few schools. These schools still follow the pattern of the points, but there were a handful of schools out here that sort of stood by themselves. Some of the larger schools where the number of loans was rather large and therefore the loan value was large. We might denote that there were a handful of large schools. And again, for this one, we might even consider breaking up the data set and looking at smaller community colleges versus larger four-year schools. This was arm span versus height again. And really, when you look at those points, I don't really see anything too unusual with this one. If you happen to have a person, I'm going to add a dot just to, we add a person there whose arm span's not very big, but they're rather on the tall side, we would denote that that point's an outlier. But as this one is sort of exists here, nothing really unusual. So that would be the fourth thing we would say. No unusual features about this graph. And then the last one, sodium versus grams of fat. Sometimes when your relationship is weak, it gets really hard to talk about outliers because you almost start to want to call a lot of these things sort of outliers. I don't really see anything unusual with this either, aside from the fact that this is an extremely weak relationship. So nothing too unusual that's very far apart from the rest of the points. All right, so now we've mentioned four things. We're going to look at a couple more scatter plots. And for each one of those, you should practice writing down the 4 points that we mentioned for each one. So this one, we have data on 100 best values in public colleges. We are looking at their admission rates is the X variable. We're trying to see if we can use their admission rate to predict their four-year graduation rate. And this is a scatter plot of 100 schools. So the first thing we want to comment on is the form. So when we look at this, do we see a pattern that fits a straight line, not a straight line, or just sort of a random scattering of points? This one, I would probably say that there's no relationship. If you wanted to say there was one, you might say there's a really weak relationship, especially if perhaps you cover those points up. You could say there's a really weak relationship that goes this way, but I would probably say no relationship. At best, it's an extremely weak relationship. Once you say no relationship, then once you say no relationship, then you really don't have a strength to that. There really is no direction. It's kind of hard to talk about outliers if there's no relationship. So I would probably call this no relationship. If, on the other hand, you had decided we're going to go with a linear relationship, sort of looking like this. If we call this linear, the direction would be negative, and the strength would be extremely weak. And if we call this a negative, linear, extremely weak relationship, we may then sort of point out that there were a couple of points down here that had lower admission rates and lower graduation rates that didn't quite fit the pattern of the rest of the points. So we might point out that potentially those are outliers. Now you'll notice with this one, in the beginning I said I'd really say no relationship, and then okay, you could have called this maybe weak, negative, linear. Some of these, there's not like one perfect answer. It's mostly, can you justify your answer? And make sure, again, that you hit on all 4 points. Unless there's no relationship, then there's really nothing else to say. So that's the first one. Okay, the second scatter plot in your course notes is this one. With this data, we're looking at earthquake data from Japan. And the X variable, the predictor variable this time, is the number of stations reporting earthquake activity. And we're using that to help predict the magnitude of an earthquake. And this one, if we look, this one definitely looks like there's much more of a pattern to the points than there was in the last one. If we kind of cover up that point for just a second, if we ignore that point, I would say that there's a definite linear trend to this set of data. So we could say this is linear. As the number of stations increase, so does the magnitude, and so this is positive. The strength of the relationship looks fairly strong. You could call it moderate or strong to moderate. And we kind of gave away the fourth item at the beginning. There's definitely an unusual observation with this one. This earthquake that had a magnitude of 8.9 would be an outlier. And so, again, make sure you comment on 4 things. The relationship looks linear, positive, pretty strong or strong to moderate, as the points are pretty tight around that line. And there's clearly an outlier with this one. Okay, one more. The last one. This is a mold count data set. We are looking at the hours on the x-axis. This is the hours since beginning to grow mold in a petri dish. And on the y-axis, we have the mold count. So we're using the amount of time as the predictor of the amount of mold. And with this one, there's definitely a pattern to these points, a very clear pattern, but the pattern is not a straight line this time. It almost looks like you could perfectly connect these points. Almost looks like an exponential type relationship here. So definitely a relationship. This time the form's not linear. This would be non-linear. So definitely do not describe this as a linear relationship. This does not form a straight line. There's clearly a curve to this. The direction's still positive. The strength of this is incredibly strong. Those points, now we're not talking about how strong they are compared to a straight line, but compared to that curve, it looks like a pretty almost spot-on relationship with that there. And we don't really see any outliers. But do not describe this one as linear. When we go on and we form models, eventually if your relationship looks like a straight line, we're going to fit a straight line to that data set. You would not want to do this with one like this. This is definitely an example of a relationship that's non-linear. But clearly there's something going on between the x variable and the y variable with this one. This is not no relationship, just a non-linear relationship. And I believe that that's the end of this lesson.